This is Jose Merino, Editor-in-Chief of the Neurology family of journals. The Neurology podcast provides practical information to neurologists and other clinicians to help them provide better care for their patients. Thanks for listening and have a great week.
Hey, this is Jason Crowell. Thanks for listening to today's Neurology podcast. Today we have Nico Dosenbach joining us. Nico is a return visitor to our podcast. He is a professor of neurology at Washington University School of Medicine in St. Louis. We have had him on the podcast several times before in the past. Most recently, in May of 2023, we invited him to join us today to discuss a paper that was published, which he is a co-author back in January 2nd of 2025. And the title of this paper is The Brain's Action Mode Network. This was published in Nature Reviews Neuroscience. Nico, thank you for joining us. Really appreciate it.
Thanks for having me.
All right. So you've joined us before in the past to talk about brain networks, and that's what we're discussing again today. So please forgive my ignorance because I've listened to your podcast before, but I just want to make sure I understand. So if you wanted to measure my brain networks, can you get into the weeds a little bit about resting state functional connectivity? How do you get that data?
Yeah, all we would need to put you in a reasonably modern MRI scanner and run a standard fMRI sequence, so blood oxygenation level dependent pulse sequence. And we would ask you to do nothing. You do whatever you want, but nothing specific. Usually there's a little right fixation plus sign on the screen in relative dark, but you could really, if you want to, close your eyes or look into the darkness, or you can turn the lights on. But the idea is that's the resting state. It's supposed to be the baseline of your brain, awake, but not doing anything specific. And that's all we need. It's easy to collect, and it's easier to collect in patient than tasks. And then the rest is a bunch of post-processing. Essentially, we're looking at the correlation structure of spontaneous fluctuations in that signal, and that's how we can find the functional networks. It looks like there's about 15 to 20. You can argue about how finely to subdivide them. They're in every person, and if you have enough data on a given person, you can find them in any person. And there's growing evidence that they seem to be important, and if they're disrupted in any way, it causes neurological, psychiatric problems in different ways. So yes, functional networks defined by resting state functional connectivity, that's mostly what I talk about.
So we're going to be talking about the action mode network, but out of curiosity, can you give us some, you said 15 to 20, depending on how you divide them. What are some examples of other networks that we could have talked about today?
First one to be talked about, the original one and probably the most famous one, is the default mode network. That around 2003 to 2005, that first became something. Hearing about the default mode network from Mark Rakel is what drew me into this kind of work. I was at the very beginning of my PhD then. That's I would say, the antipole to the action mode network. It's the set of regions in the brain that when you're not doing anything, you're slightly more active than the rest of the brain. And parts of the hippocampus are part of this network. And so it's thought to be important for self-referential memory and, mental time travel, things like that, when you're sort of thinking about yourself and your life. And there's probably other functions to that resting state, right? That probably not about what you're thinking about. There's maintenance and encoding types of processes happening too.
So in this paper, again, one of the points that you make before we talk about this action mode network, one of the points you make is that previously this field in which you study was it operated by defining these networks anatomically. And though you make a pretty clear argument in this paper that defining networks by their function rather than their anatomy offers some advantages. Can you expand on that?
I'm a disciple of the inside-out approach, where you start with the brain and you try to let the brain data that you can collect tell you what's there, versus the outside-in approach, which would be you start with some strong concept you have, like a psychological idea. Like, I think there's a thing called cognitive control, and I'm going to look for its correlates, right? Because you usually end up finding something, but that's heavily influenced by what you thought was going to be there in the first place. So with the resting state functional connectivity approach, you don't have to make any assumptions. You don't have to ask the participant or patient to do anything. And I don't even think that anybody was expecting these networks, which is why they were for a long time sort of ignored and thought they were artifacts. It was a big surprise, actually. And those are often the best findings when, it doesn't make any sense, but the data keeps showing you the same thing. And eventually you deal with it and you say, well, this is a real thing in the brain. What's it for? What's it doing? How does it affect behavior? How does it affect brain health and brain disease? So it's a brain first, data-driven philosophy.
Okay, so with that as context, tell us about the brain's action mode network. What does this do?
Part of the reason for writing this is that we're renaming it. We found this in 2007 and didn't really know exactly what it did and gave it an anatomical name, singular opercular network. Over the last 17 years, we've learned a lot about this network and also realized that wasn't a good name because there's other networks that had very similar anatomical distribution. And so there was a ton of confusion and people would use the same name for different networks. And it's made a mess of the publications. And so we thought it was important to give it a much better name. And we wanted to capitalize on the fact that the default mode network is well known and its function is pretty well described. So the action mode network is the most strongly anti-correlated with the default mode network. And there seems to be this yin-yang almost relationship where the action mode network is always slightly more active when you're doing something specific, but it doesn't matter what. And then the default mode network is always slightly more active when you're not doing anything specifically, right? And the idea is that there's these behavioral states of goal-directed behavior and rest, and there's corresponding brain modes of the default mode and the action mode. And so our work that we kind of summarize and work with others in this perspective has shown that somewhat surprisingly, there seems to be a full stack network in the brain that goes from prefrontal cortex, involves premotor and motor regions, and deep structures in the putamen, and all the way down into the brainstem. That's not organized in motor versus cognitive. It's actually all the functions related to you actually doing something, all the way from the most abstract planning, which what people would think is in the anterior prefrontal cortex, area 10, like frontal pole, to actually moving. Which makes sense if you think about why we have a brain in evolution and our phylogenetic lineage in brain evolution is right. We don't have the brain to move. Like you move during a seizure, that's not very helpful. Or you can pointlessly swing your arms. That's not what the brain's for, right? It's for goal-directed behavior. You're achieving some behavioral goal, which pretty much always involves moving, even speech, right? You moving your vocal cords in your mouth. So we realized that the brain is sliced differently than I used to think, and maybe even a lot of neurologists are taught or thought. One analogy I use, it's like the library is organized by topic, not alphabetically, right? And the topic for the action mode network is we're actually going to do this thing, but it involves extremely abstract things that people call thinking, all the way down to actual whole body movement plans and like executing movements. So once we started thinking about the brain in this way, we started realizing that a bunch of other functions that seem to map onto the same brain network, but used to not make any sense to us. Once we started thinking about it as not like, oh, is this a cognitive network or why are there motor regions in this network? We started thinking about it as an action mode network. We realized that, for example, it's got some arousal functions, like the central median nucleus of the thalamus is part of it. The first thing that happens when you're going to do something is you arouse, right? I mean, you know that it's harder to fall asleep when you're on call and moving around and doing stuff than when you're sitting on a chair, right? So if you think about action, then of course, also having not just movement and having arousal in there in the same circuit starts making sense. And really, the brain is probably organized according to categories that we just didn't think of. So we gave it a bunch of different names. But really, in some ways, it's like it's doing what it's supposed to do, but we just didn't have the right words. So arousal loads onto it. The other one that was a surprise for a long time we didn't know what to do with was pain. I now think as pain as the most salient action feedback that you potentially have to operate on quickly. So it's on the same circuit as actually executing your actions and planning them. If you're reaching for something, then you hit a thorn, like you immediately have to pull back and make a new reach plan to grab the apple or whatever, right? And so once we started realizing that the network was about the action mode, that made more sense. And so it's like we're essentially kind of resorting, I think, how we used to bin brain organization. And this action mode network is a very important one because it's probably an ancient network in evolution because the brain is mostly for action, right? If something the brain does doesn't result in action in some form, even indirectly, like evolution is blind to it, right? Because it can only select on what you're doing. And so it's closer to the outputs and it's closer to actually controlling behavior. So there's papers coming out and we've got some unpublished data, but there's a series of a lot of what people still call movement disorders seem to actually load onto the action mode network.
So if we distill it down to there's the action mode network where there's going to be something done, and then you talk about in the paper that this, as you said just now, the yin and the yang with the default mode network, then where do these other networks fit in? Because it seems like those seem complementary and exclusive to one another. Where do the other networks fit into this organization?
They're sort of in between in my thinking, right? I think the network structure at this highest level, these are macro networks, right? Covering the whole brain in essence, is partially parallel. It's fairly parallel, but it can't be completely parallel, of course, right? because every part of the brain can sort of interact with every other part in some ways indirectly. And in these partially parallel networks, I was just talking to my colleague, Evan Gordon, who's on this article about this. It's like we have these words like thinking, right? Or even cognition, because externally, like the way we observe it, or even movement, right? It all looks like it's the same thing. But what we call thinking probably comes in 5 or 6 flavors in terms of brain networks, where computationally there's similar processes happening in parallel, but towards different ends. And so, for example, another network that I've been studying, I'm really interested in, that we don't totally know exactly what it does yet, so it still has an anatomical name, the frontoparietal network. I think one of the differentiating factors compared to the action mode network is it's literally like more abstract, right? Meaning the thinking you do with the action mode network, it's for things you're actually going to do, right? Purely sort of abstract things, maybe doing math in your head, not that people do that or whatever, that you don't have a concrete plan that maybe indirectly will influence your behavior, but you're not going to do anything about. Those would be in the frontoparietal network. Things that are self-referential, where you're thinking about your 8th birthday or how something made you feel earlier, right? That would be the default mode network. So what's special about the action mode network is, and we haven't published this, but you can even do some experiments where just like you're just thinking about doing something, but you're not going to do it. It doesn't get the action mode network because that you're not actually going to do that, right? So until we saw the data, like I don't think I or anybody thought that abstract cognitive processes would be so closely tied to movement and that there'd be sort of multiple parallel versions for slightly different ends. Like an example that's maybe more accessible than these abstract things is like, right, it's been shown that when a sound comes in the ear, it's simultaneously processed for speech perception and just general hearing. And that's one of the reasons that you immediately also process every sound for speech in parallel is one of the reasons that we're so good at understanding spoken language. If we did it serially, we'd be too slow, right? And so it seems like you're also always processing things for action, partially parallel with more abstract versions of maybe the same basic processes. I like to think about this. There's really not evidence for this, but I feel like everybody, especially in academia and medicine, knows this, that there can be a disconnect between people of action and people who like to think about things. Could be that it's because these things are sort of on parallel networks. Just because you have a brilliant thought doesn't necessarily mean that you feel like you need to do something about it. And there are definitely people who prefer doing things right away over cogitating about them for a long time. And there's probably other networks, or we think there's other networks that we know about that also do very complex higher order cognitive things as part of their, I would say, loop or circular processing. And for some of them, we're still trying to figure out what the special flavor is. Because all these networks are in parallel in the sense that they're immediately spatially adjacent to each other in different parts of cortex, right? So there'd be like patches in the insula or prefrontal cortex or the cingulate, where the cytoarchitecture is very similar. So we know the cellular machinery for computation is the same. So what we think is that they run fairly similar processes, but just for different overall behavioral goals. If that makes sense.
Could you talk about how, or at least give us an idea of how one could imagine neuromodulation being used with these networks? So, we've got focused ultrasound, we've got these brain stimulators, we have transcranial magnetic stimulation. How conceivably could one might argue that neuromodulation could be employed to affect these networks one day?
Oh yeah, so this is something we're working on actively, super excited about, and lots of collaborators are too. And there's data coming in, mostly not published yet. That's very exciting. And so there's several avenues where there's clinical data from neurological patient populations suggesting that neuromodulating specifically the action mode network could be helpful. So, and some are more obvious. So there's Tourette's, which seems like a problem with letting an action that was maybe supposed to be inhibited sneak out. So there's good evidence there. And that's been recently published. And there's a recent paper on dystonia where it looks like the action mode network related somatocognitive action network in the motor cortex is responsible for axial dystonia, and then classical motor cortex is related to foot or hand or mouth dystonia. So that gives you new hypotheses about how to use the DBS, so cortical stimulation dystonia pain. So there's always been this treatment of motor cortex stimulation that worked for severe chronic central pain, and it didn't make any sense. Well, it looks like that's because those are actually regions that are in M1 that are connected to the action mode network and also carry some either pain signals or have pain regulatory capabilities. Other ones would be, we're interested in would be Parkinson's, right, which is definitely more of an action disorder than a pure movement disorder, given this mixed bag of symptoms. It's sort of a general reduction in action voluntary behavior, abulia, apathy. It looks like in psychiatric disorders with psychomotor slowing that the action mode network might be involved in that. And then one that's a little different, but we think also makes sense, is the arousal effect of the action mode network could be helpful in epilepsy, including generalized epilepsy, where essentially I call it a benzo button at a conference. And people like the idea that, I used to think this was nonsense until the data told me otherwise, but this idea that you, even if it's a generalized epilepsy, that there could be focal nodes that you can stimulate that change the excited to inhibitory ratio throughout cortex and essentially dampen down neuronal excitability globally in a non-specific way. Those nodes also seem to be linked to the action mode network because you need to arouse to do stuff. And that's what happens, right? So bunch of, I would say, strong hypotheses to go after neurological and psychiatric disorders with new hypotheses and new targets for neuromod. And the one I'm excited about is it looks like, and there's lots of proponents of these ideas, right, of sort of circuit therapeutics and network therapies, that if you can identify the entire circuit, the network, you can go after cortical targets, which are, of course, accessible to non-invasive neuromodulation like TMS, or you could just put electrodes on the surface, which is still easier. I'm not a surgeon, but that's what it seems like, than putting in depth electrodes where you have risk of bleeding or something. So I think for a lot of these indications, we're working on surface targets for less invasive neuromodulation, and then also new targets because we now know the entire network. And the one thing I've been worried about is I'm very suspicious of things where they're sort of important for everything that can't possibly be. So this might look like the action mode network is sort of a grab bag. It's not going to be useful for all things, not at all. And I think it's now making more sense. It's not really a grab bag if you think about it as action related, then the combination of arousal, pain, cognitive aspects like will to act and planning, and the actual movement execution actually all fit under this umbrella. And the reason we used to think they don't fit together is because we had just made up categories from observing behavior, and they just don't match that well onto how the brain's actually organized.
That's very interesting, Nico, and I appreciate you explaining that for us. I admit these networks are not something I think about day to day, in patient care, but it's easy to see, as you've just pointed out, the potential translatability of this research, especially with all these neuromodulatory tools that are increasingly available.
The one that fascinates folks that aren't even neurologists more is this idea, right, of will or motivation even, which can get very philosophical quickly. It does seem that the most prefrontal, including on the midline regions, like in the cingulate, the action mode network, sort of is where you initiate voluntarily doing something when nobody's telling you to. And so we've been having fun talking about that and the possibility, we could neuromodulate willpower into people or make you stick to the plan kind of stuff. That's a little sci-fi maybe, but at least theoretically possible. That's sort of the non-neurologist, even if they don't care about, dystonia or Tourette's or whatever, they find that fascinating. And then, who doesn't wish they had more willpower?
Sure. I know I do.
Yeah, me too.
Well, I hope you all out there listening find the willpower to read this paper. Again, it was published in Nature Reviews Neuroscience on January 2nd. The title of the paper is The Brain's Action Mode Network. And we've been joined by Nico Dosenbach from WashU. Nico, thanks for joining us. We appreciate it.
Thank you.
This is Stacey Clardy, your podcast editor. If you've enjoyed the podcast, please take a few moments to subscribe, rate, and review the Neurology Podcast through Apple Podcasts, Google Podcasts, Spotify, or wherever you listen. And remember, you can always head to neurology.org/podcast for our full list of past episodes. Or you can also search by keyword in your podcast app for any neurology-specific topics you want to learn about.